Physics is our language for explaining the universe, its stars, galaxies, and the invisible forces that bind it all together. For most of the cosmos, this language works perfectly, predicting motion, energy, and gravity with stunning accuracy. But when we push physics to its limits, toward the dawn of time or the farthest reaches of space, it starts to falter. Equations that once made sense begin to break apart, and the familiar laws of nature twist into something unrecognizable. At these extremes, the universe stops behaving like we expect, revealing cracks in our understanding and hinting that reality itself might be far stranger than we can yet imagine. And if you want to uncover the full story, then watch this video till the end and subscribe to the channel. Let's begin. As we move from the mystery of physics breaking down to the question of where this breakdown begins, we come face to face with one of the most misunderstood ideas in cosmology, the so-called edge of the universe. When people hear that phrase, they often imagine a cosmic border, some vast wall or boundary beyond which there is only darkness or nothingness. But in truth, the universe doesn't end anywhere. There's no edge you could reach, no cosmic cliff to fall off. What scientists really mean by the edge is something far subtler. It's the limit of what we can observe. This boundary isn't physical, it's temporal. Because the universe is about 13.8 billion years old, light from regions farther away than that simply hasn't had enough time to reach us yet. The speed of light, though unimaginably fast, is finite. So our vision of the cosmos is constrained by time itself. The edge is really the edge of the observable universe, the farthest horizon from which light, radio waves, or any form of information has had the chance to travel across expanding space to our telescopes. Beyond that boundary, the universe doesn't stop. It just becomes invisible, hidden by the finite age of reality and the constant stretching of spacetime. So when cosmologists talk about looking to the edge, they're not searching for a wall. They're staring into deep time, trying to glimpse the oldest light still reaching us since the Big Bang. It's a limit of knowledge, not of existence, a cosmic horizon drawn not by matter, but by the very nature of light and time itself. Now that we've defined what the edge truly means, the next natural step is to understand the observable universe, our cosmic bubble of visibility. Imagine it as an enormous sphere centered around you, stretching in every direction for about 46 billion light-years. That's not because the universe is only that large, but because that's as far as light has managed to travel to reach us since the Big Bang. Every second, light from distant regions continues to arrive, slowly expanding our field of view. In other words, the observable universe is not static, it's growing. Not because the universe itself is expanding into something, but because space itself is stretching, carrying galaxies ever farther apart. This stretching of space has a strange consequence. While the light from distant galaxies travels toward us, the universe continues to expand during its journey. That means the light we receive has been stretched in wavelength, a process known as cosmological redshift. The farther away a galaxy is, the more its light is stretched, turning visible light into infrared, then into microwaves, as it fights to cross an ever-expanding ocean of space-time. What we're really seeing, then, isn't just distance, it's history. Each photon of light carries the story of a younger universe, allowing us to literally look back in time billions of years. And because space continues to expand faster than light can travel at great distances, some galaxies we can see today will eventually slip beyond our view forever. They aren't moving through space faster than light. Rather, space itself is stretching faster than light can keep up. It's a haunting realization. Much of the universe will one day fade from view, leaving behind only the galaxies bound to us by gravity. The observable universe, then, isn't the whole story. It's just the visible fraction of a reality far vaster than we can ever perceive. Beyond that limit, space continues indefinitely, possibly infinitely, filled with galaxies, matter, and light that will forever remain beyond our reach. As we journey from the observable universe into the deeper fabric of reality, we arrive at one of the greatest confrontations in all of science: the conflict between Einstein's general relativity and quantum mechanics. These two pillars form the foundation of modern physics, and yet, when we try to make them coexist, they seem to speak entirely different languages. Each governs a different scale of existence beautifully. But when the cosmos pushes both to their limits, the two sets of laws collide in ways that reveal the deep incompleteness of our understanding. Let's begin with general relativity, Einstein's grand masterpiece. Published in 1915, it replaced our old Newtonian view of gravity as a simple pulling force with something far more elegant: the warping of spacetime itself. According to relativity, massive objects like stars, planets, and galaxies bend the very geometry of space and time around them. This curvature is what we experience as gravity. The sun doesn't pull Earth through invisible strings. Instead, it creates a dent in space-time, and Earth simply moves along the curved path dictated by that dent. Everything massive shapes the cosmic stage it occupies, and in turn, that stage dictates how everything moves. Relativity explains the large-scale structure of the universe astonishingly well. It predicts the motion of planets, the bending of light around massive bodies, gravitational lensing, the expansion of the cosmos itself, and even the existence of black holes, where gravity becomes so intense that not even light can escape. It gives us the framework to understand the evolution of the cosmos from the Big Bang onward, mapping how matter clumps into galaxies and how space-time stretches like a cosmic fabric. But then there's the other half of physics, quantum mechanics, the bizarre and brilliant framework that governs the microscopic realm. It describes atoms, subatomic particles, and the strange rules they play by. Particles can exist in multiple states at once, superposition. They can influence one another instantly across vast distances, entanglement, and they don't have definite properties until they're observed. Quantum theory is not intuitive. It defies our everyday experience, but it is extraordinarily accurate. It explains how the sun shines, how your smartphone works, and how the universe at its smallest scales is ruled by probabilities, not certainties. These two theories, in their own domains, are unmatched in precision and predictive power. But here's where things start to fall apart. They fundamentally disagree about how the universe works when both the very large and the very small collide. This happens in extreme conditions, near black holes at the moment of the Big Bang, or at the Planck scale, where distances and energies become unimaginably intense. In relativity, space-time is smooth and continuous, a flexible fabric that can stretch or bend but never tears. In quantum mechanics, however, everything comes in discrete packets. Energy, matter, and even information behave as quantized entities. When you try to apply quantum rules to space-time itself, relativity's continuous smoothness breaks down. Space and time, instead of being calm and flowing, become jittery, uncertain, and full of fluctuations. At these scales, space-time is expected to foam with quantum uncertainty, bubbling and flickering with temporary virtual particles popping in and out of existence. Now, here's the paradox. Relativity insists that gravity is a geometric property of space-time, but quantum theory treats forces as arising from particle exchanges, gravitons in this case. When physicists try to quantize gravity the same way we do for electromagnetism or the nuclear forces, the math explodes into infinities that can't be renormalized, meaning the equations lose all sense and yield nonsense results like infinite energies and zero probabilities. This tension is not just mathematical, it's philosophical. Relativity describes a deterministic universe. If you know the present, you can predict the future. Quantum mechanics, by contrast, describes a probabilistic one. Reality is fundamentally uncertain until it's measured. These aren't just different flavors of truth. They are incompatible at their cores. At ordinary scales, we can use each law independently. Relativity for stars, planets, and galaxies. Quantum mechanics for atoms, particles, and photons. But at the edges, near singularities, or the instant of creation, both must apply simultaneously. That's when physics starts to act weird, because the two frameworks refuse to merge cleanly. The gravitational field of relativity becomes infinite, while the uncertainty of quantum mechanics becomes total. This conflict is sometimes called the quantum gravity problem, the greatest unsolved mystery in theoretical physics. Scientists have spent decades trying to unify the two frameworks into a single, consistent theory that can describe the universe under all conditions, from the quantum foam to the cosmic web. Candidates like string theory and loop quantum gravity have emerged, but none yet stand as a final answer. Each provides glimpses into a deeper layer of the cosmos, where space-time itself may not be fundamental, but emergent, like waves rising from a deeper, hidden ocean of reality. In a sense, the battle between relativity and quantum mechanics is not just about equations. It's about the nature of truth itself. Does the universe run on cause and effect, or on probabilities and potentials? Is space smooth or pixelated? Is time continuous or quantized? These are not small questions. They are the keys to understanding why physics begins to act so strangely when we stare into the cosmic abyss, toward the beginning of time or the edge of everything we can see. And so, at the intersection of the vast and the minute, where galaxies meet quarks, the laws that govern our universe begin to clash. And it is within that clash that the next revolution in physics waits to be discovered. As we push our gaze toward the farthest reaches of the observable universe, we run headfirst into one of cosmology's most puzzling challenges, the cosmic boundary problem. It's here, at the very limits of what we can see, that even our most trusted measurements begin to blur. Our tools of understanding twist under the weight of cosmic expansion, and the very concepts of distance, time, and even reality itself become uncertain. When astronomers point their telescopes toward the deepest parts of space, they're not just looking far away, they're looking back in time. The light that reaches us from those distant galaxies has been traveling for billions of years, crossing an expanding universe along the way. By the time it arrives, that light has been stretched by the expansion of space-time itself, shifting its color toward the red end of the spectrum. This is what we call cosmological redshift. The greater the redshift, the farther back in time we're looking. But here's where the trouble begins. At extreme distances, space isn't a static stage. It's expanding dynamically, so what distance even means becomes slippery. A galaxy we observe today, as it looked 13 billion years ago, hasn't stayed where it was. Space has stretched, and that same galaxy might now be over 30 billion light-years away. Our instruments can measure redshift with astonishing precision, but translating that redshift into actual distances depends on models of cosmic expansion, models that themselves rely on assumptions about dark energy, dark matter, and the curvature of the universe. If any of those assumptions shift even slightly, our sense of scale can warp dramatically. This leads us directly into the cosmic boundary problem. Near the limits of observation, the edge of the observable universe, space-time itself is so stretched and curved that our ability to define where and when starts to collapse. Light doesn't travel through a flat, calm space-time, but through one that's continuously warping, expanding, and twisting under the influence of gravity and dark energy. The further we look, the more this curvature distorts everything we see. Galaxies appear frozen in time, smeared by gravitational lensing, and their light dimmed by unimaginable distances. Even the speed of light, though constant locally, interacts with expanding space in ways that make distant regions seem to recede faster than light itself. At the boundary, these distortions become so extreme that our measurements begin to lose meaning. A simple question like, "How far away is that galaxy?" stops being simple. Distance in cosmology isn't one thing. There are multiple definitions: comoving distance, proper distance, luminosity distance, angular diameter distance, each giving a different number depending on how you define time and motion in an expanding universe. At cosmic scales, the geometry of space-time and the passage of time itself are no longer fixed. They depend on where you stand, how the universe has expanded since the light left its source, and what model of physics you're using to interpret it. But there's an even deeper layer to the boundary problem: the limits of information. Beyond a certain redshift, around Z equals 1100, we reach the surface of the cosmic microwave background radiation, CMB, the oldest light we can observe, emitted roughly 380,000 years after the Big Bang. Beyond that, the universe was opaque, filled with a dense plasma where photons couldn't travel freely. So no matter how powerful our telescopes become, we cannot see beyond this last scattering surface. It forms a literal wall of light, not a physical edge, but an informational horizon. Beyond it, the early universe remains hidden, inaccessible to direct observation. And yet, even within that horizon, the distortion of space-time continues to complicate what we think we know. The expansion of the universe isn't perfectly uniform. It's influenced by the distribution of matter and energy. Massive galaxy clusters act as gravitational lenses, bending light from even more distant galaxies into arcs and rings. Time itself runs differently, depending on gravitational potential. Clocks in deep gravitational wells tick more slowly than those in the cosmic void. Near the boundary, these effects compound into a web of uncertainty, where space, time, and perception intertwine. To make matters stranger, the farther we look, the younger the universe appears, not just in age, but in structure. Galaxies were smaller, stars burned hotter, and cosmic matter was more tightly packed. The edge isn't just far away. It's a view into the ancient past, where the laws of physics might not have fully stabilized into the forms we know today. So as we stare toward that distant horizon, we aren't just reaching a spatial limit. We're touching a temporal boundary, where the universe's youth and our incomplete understanding converge. In the end, the cosmic boundary problem teaches us something profound. Our perception of the universe is always mediated through the lens of space-time itself. And space-time, far from being a passive backdrop, is an active, dynamic participant in shaping what we see. The more we stretch our gaze, the more it stretches us in return, forcing us to confront the uncomfortable truth that reality, at its edges, may not be what it seems. The boundary isn't just out there in the darkness between galaxies. It's built into the very structure of the cosmos, a horizon of understanding that retreats each time we take a step closer. When we trace the cosmic story backward, rewinding billions of years of expansion, galaxies drifting apart, and space stretching wider, the universe begins to shrink in our imagination. Every structure, every cluster of stars, every atom collapses toward a denser, hotter, and smaller past. If we keep reversing time far enough, we eventually reach a point where our mathematics begins to fail. A place where density, temperature, and curvature of space-time soar toward infinity. This is what physicists call the Big Bang singularity, the hypothetical moment when everything in the universe, space, time, matter, energy, and the very laws that govern them, were compressed into a single, unimaginably small state of infinite density. To understand why this singularity appears, we need to look at how Einstein's general relativity describes the universe. According to relativity, gravity is the result of space-time curvature caused by matter and energy. The more mass and energy you pack into a region, the more space-time bends. But when we try to describe the entire universe contracting back in time, this curvature becomes extreme. The equations tell us that, as we approach the beginning, the density and curvature become infinite and space-time collapses to a single point. This point isn't just dense, it's a geometric breakdown of space-time itself. There's no before the singularity, because time as we understand it doesn't exist prior to it. It's a mind-bending idea. The universe didn't explode into space and time. It was the birth of space and time themselves. The Big Bang wasn't a detonation in a pre-existing void, but the moment when the fabric of space-time began expanding from a state of infinite compression. Asking what came before the Big Bang is, in this framework, like asking what's north of the North Pole. Our very notion of direction and sequence stops making sense. However, there's a catch, and it's a big one. The singularity predicted by general relativity might not be a real physical object. Instead, it's a mathematical warning sign, a signal that the theory itself has reached its limits. Infinities in physics usually mean that something deeper is missing from our equations. When the density and temperature of the early universe become too extreme, quantum effects, those described by quantum mechanics, can no longer be ignored. But Einstein's theory doesn't account for them. Relativity treats space-time as a smooth continuum, while quantum mechanics tells us the universe, at its most fundamental level, is grainy and uncertain. So at the Big Bang, where both gravity and quantum effects are enormous, our two great theories collide and break down. To put it simply, the singularity is where physics itself stops working. Our equations can describe the universe mere fractions of a second after the Big Bang, down to about 10 to the minus 43 seconds, known as the Planck time, but not the moment itself. Beyond that boundary, our current understanding dissolves. We can't say what the universe looked like, what caused the Big Bang, or even whether cause is a meaningful concept there. And yet, this breakdown has led to some of the most exciting questions in cosmology. What if the singularity wasn't truly infinite? What if it was a quantum seed, a finite but unimaginably dense state governed by quantum gravity? Some theories, like loop quantum cosmology, suggest that before the Big Bang, there may have been a contracting universe that bounced into expansion, a big bounce, not a beginning. Others, like string theory, propose that our universe could have emerged from the collision of higher dimensional membranes, or branes, in a vast multiversal landscape. Still, all these theories share a haunting truth. The singularity marks the edge of our knowledge. It's not just the beginning of time, it's the end of predictability. It's a boundary where our mathematical descriptions fail to capture what's real, and where the familiar notions of space, time, and causality dissolve into something beyond comprehension. So when we speak of the Big Bang, we're really describing the limit of our vision, a horizon of understanding where our models lose meaning. The singularity may never have existed as a physical point. It may instead represent a transition from something timeless and unobservable into the structured reality we now inhabit. And that's what makes it so profound. The Big Bang singularity isn't just a scientific puzzle, it's a philosophical one. It forces us to confront questions that blur the line between physics and metaphysics. What does it mean for time to have a beginning? Can something emerge from nothing? And if the laws of physics didn't yet exist, what could possibly have given rise to them? At the singularity, we are staring into the ultimate mystery, the place where the universe began to be, and where our understanding ceases to comprehend. As we move from the Big Bang singularity deeper into the realm of extremes, one truth becomes unavoidable. Classical physics collapses under the weight of infinity. The phrase, "the laws of physics break down," isn't poetic exaggeration. It's the literal consequence of our mathematical frameworks running into situations they were never designed to handle. Both the Big Bang and black holes represent boundaries in our understanding where classical ideas of space, time, and matter lose coherence, and the familiar equations that govern the universe suddenly stop making sense. To understand why, we need to revisit what classical physics really means. Classical physics encompasses the frameworks developed before the rise of quantum mechanics. Newton's laws of motion, Maxwell's electromagnetism, and Einstein's general relativity. These theories describe a world that is continuous, deterministic, and predictable. If you know the present state of a system and the forces acting on it, you can calculate its future precisely. The universe, under classical laws, is a cosmic clockwork, every gear turning with perfect mathematical precision. But this smooth predictability only works so long as quantities remain finite. Finite masses, finite energies, finite densities. When those numbers blow up to infinity, as they do in the heart of a black hole, or at the birth of the universe, the entire machinery of classical physics grinds to a halt. Let's start with the Big Bang. As we rewind cosmic history, relativity tells us that the universe's density and temperature increase without limit. But infinity isn't a number. It's a signal that the model has broken down. The equations of general relativity depend on space-time curvature, and as curvature grows infinitely large, the math ceases to describe a coherent geometry. The same happens inside a black hole at its central singularity. According to relativity, all the mass collapses into an infinitely small point, where curvature becomes infinite and space-time effectively tears itself apart. It's not that physics stops working there, it's that our description of physics stops being meaningful. Here's the key insight. Infinities are the universe's way of telling us we've gone beyond the reach of our theory. They signal that our mathematical model no longer applies to physical reality. In both the Big Bang and black holes, the gravitational field becomes so intense that quantum effects, the random fluctuations that dominate at subatomic scales, can no longer be ignored. Classical physics, with its smooth curves and continuous fields, has no language to describe what happens when gravity and quantum uncertainty intertwine. Take, for instance, the singularity inside a black hole. According to relativity, once matter crosses the event horizon, the boundary beyond which nothing can escape, it must collapse inward indefinitely, crushed by gravity into an infinitely dense point. But quantum mechanics says that nothing can be perfectly localized. Every particle has an uncertainty in its position and energy. Trying to compress matter into a singular point violates this principle. Somewhere between those two regimes, our physics simply stops being self-consistent. That's why physicists say the laws of physics break down. It's not that nature stops working, it's that our equations stop describing it. The universe doesn't care whether our mathematics can keep up, it simply is. What fails is our ability to translate that reality into coherent, finite, predictive equations. Inside black holes, for example, time and space trade roles. What we think of as time becomes a direction pointing toward the singularity, inescapable, inevitable. No observer can stand still. No event can unfold in the usual sense. Causality itself, that comforting chain of cause and effect, collapses. Similarly, at the Big Bang, time doesn't start in the classical sense. It emerges out of a state where time had no meaning. The singularity is not a moment within time. It's the condition from which time itself arises. Classical physics, built on the assumption of a continuous, measurable flow of time, cannot handle a scenario where time itself breaks down. Another place where classical physics fails is in its treatment of energy density. As we approach singularities, energy densities become infinite in theory. But infinite energy would instantly destroy the fabric of space-time. Nature, evidently, doesn't allow infinities to actually occur. Instead, the infinities appear because our models are incomplete. Quantum physics suggests that, at incredibly small scales, energy and space might come in discrete quanta. If that's true, then infinite density is physically impossible. Space and time themselves would have a smallest possible unit. Classical physics, which assumes a continuous fabric, can't see that limit, so it runs straight into the impossible. This breakdown of classical physics has been one of the most profound realizations in the history of science. It tells us that our universe, no matter how elegant its large-scale order appears, is built on a foundation of chaos and uncertainty at the smallest scales. The edges of our equations, black hole cores, the birth of the cosmos, aren't just curiosities. They're warning signs that something deeper is hidden beneath the surface, waiting to be discovered. In many ways, the failure of classical physics at these extremes has been a gift. It's driven physicists to search for a theory of quantum gravity, a framework that can reconcile the smooth space-time of relativity with the jittery probabilities of quantum mechanics. Such a theory would eliminate the singularities, replace infinities with finite, quantized structures, and reveal what truly happens when the universe compresses itself into its most extreme states. Until then, we remain on the threshold, able to describe the universe beautifully in almost every regime, but blind at its deepest cores. The breakdown of classical physics isn't a defeat, it's a signpost, pointing toward the next great revolution in our understanding of reality. It's the universe's way of saying, "You've come far, but this is only the beginning." As we pass beyond the crumbling edge of classical physics and peer into the earliest moments after the Big Bang, we enter a domain ruled entirely by quantum uncertainty, a realm so chaotic, so fundamentally unpredictable, that reality itself flickered between possibilities billions of times each second. This is the quantum dawn of the universe, the period when everything we now see, every star, every planet, every galaxy, was nothing more than a storm of quantum fluctuations rippling through a seething sea of energy. In these first instants, just after the Planck time, the universe was unbelievably small, hot, and dense. Temperatures were trillions of times hotter than the core of the Sun, and the energy density was so high that particles and radiation were constantly being created and annihilated in flashes of quantum activity. There were no atoms, no light as we know it, not even stable protons or neutrons, only a raw quantum field of potential. In this violent haze, uncertainty wasn't just present, it was everything. At the quantum scale, the universe obeys a principle first described by Werner Heisenberg, the uncertainty principle. It states that you can't know both the position and momentum of a particle with perfect precision. The more you know one, the less you can know the other. This fundamental limit to knowledge isn't about faulty instruments. It's built into the nature of reality itself. In the earliest universe, this meant that energy and matter constantly flickered in and out of existence, creating tiny variations in density, microscopic wrinkles in the otherwise smooth cosmic field. Normally, such fluctuations would be minuscule and short-lived. In our current universe, they appear as fleeting virtual particles that emerge from the vacuum and disappear almost instantly. But in the primordial universe, something extraordinary happened: cosmic inflation. During this brief but stupendous burst of exponential expansion, space itself stretched at an unimaginable rate, possibly doubling in size every 10 to the negative 35th seconds. And as space expanded, it stretched those tiny quantum fluctuations along with it. Quantum ripples that were once microscopic suddenly ballooned to cosmic scales. Inflation took the random quantum jitters of energy density and froze them into the very fabric of space-time as tiny variations in temperature and matter distribution. These fluctuations became the seeds of structure, regions ever so slightly denser than their surroundings, destined to become the galaxies, clusters, and filaments we observe billions of years later. We can still see the imprint of these ancient fluctuations today in the cosmic microwave background, CMB, the faint afterglow of the Big Bang. When satellites like COBE, WMAP, and Planck mapped this radiation, they found tiny temperature variations, only about 1 part in 100,000, scattered across the sky. Those variations are the fossilized fingerprints of quantum fluctuations from the universe's first instant. Every star that shines today, every galaxy that drifts through space, owes its existence to these infinitesimal ripples of quantum randomness. This idea that the vast structure of the cosmos was born from microscopic uncertainty is one of the most astonishing insights in all of science. It means that quantum mechanics isn't confined to the atomic scale. It shaped the architecture of the entire universe. The grandest cosmic patterns, from spiral galaxies to galactic filaments spanning billions of light years, began as random fluctuations in a quantum field smaller than a proton. And yet, this raises a profound question. If the universe began in such chaos, how did it become so ordered? The answer lies partly in the statistical nature of quantum theory. Though individual fluctuations were random, the average behavior across vast regions of space was remarkably uniform. Inflation amplified both the randomness and the regularity, stretching quantum uncertainty into a cosmic tapestry that was both chaotic and smooth, an elegant paradox where disorder gave birth to order. In those early moments, the universe didn't yet have defined laws or constants in the way we think of them today. The fields governing particles and forces were still settling, oscillating between states as the energy of the universe cooled. Space itself may have been bubbling with quantum foam, a frothy, flickering structure where the geometry of spacetime fluctuated wildly, creating temporary pockets of curvature and energy. In this pre-geometric phase, space and time were not continuous. They were probabilistic, more like waves of potential reality than fixed coordinates. From that foam, through processes we are only beginning to theorize, stability slowly emerged. As the universe expanded and cooled, forces separated. The strong nuclear force, the weak force, electromagnetism, and gravity each crystallized into their distinct forms. The chaos of quantum fluctuations began to freeze into permanence. Where the quantum field was slightly denser, gravity took hold, drawing matter together. Over billions of years, those denser patches became the scaffolding for galaxies, stars, and eventually life itself. It's humbling to realize that everything around us, our planet, our DNA, our thoughts, arose from the randomness of the quantum vacuum. The universe wasn't born from perfection, but from fluctuation, from uncertainty, from the dance of probabilities. The cosmos is, in a very real sense, a magnified quantum event, the vast made from the tiny, the predictable born from the uncertain. But this also forces us to confront one of the most haunting implications of quantum cosmology. If our universe emerged from fluctuations, could others have as well? In some models of inflation, the same process that created our universe could create countless others, each birthed from its own random quantum fluctuation in a larger multiversal field. Each one might have different physical laws, constants, and dimensions. In that sense, our universe might be just one ripple among infinite others in a boundless quantum ocean. At the dawn of time, when everything was uncertain, the quantum vacuum gave rise to existence itself. The universe's first act was not one of order, but of probability, a cosmic coin toss that, against all odds, produced a universe capable of asking where it came from. At this point in our cosmic exploration, we've journeyed from the vast scales of galaxies to the trembling birth of the universe, where quantum fluctuations ruled everything. But now, we must take one step deeper, past even the smallest particles, into a realm so minuscule and extreme that our very concept of space and time begins to dissolve. This is the mysterious domain of the Planck scale, the ultimate frontier of physics, where space-time itself stops behaving like a smooth fabric and starts acting more like a bubbling, uncertain quantum soup. To understand the Planck scale, we first need to know that in physics, every constant, like the speed of light, c, Newton's gravitational constant, g, and Planck's constant, h, encodes fundamental limits of nature. When you combine these three constants mathematically, you get quantities that define the smallest meaningful intervals of time and space, beyond which our current physics ceases to make sense. These are known as Planck units, named after the German physicist Max Planck, who first identified them in the early 20th century. The Planck time, approximately 10 raised to the power of minus 43 seconds, is the shortest possible interval of time that can have physical meaning. Below this threshold, the very notion of before and after loses coherence. You cannot divide time into smaller chunks because, at that scale, the universe's structure becomes dominated by quantum uncertainty. Similarly, the Planck length, around 1.6 times 10 raised to the power of minus 35 meters, is the smallest measurable unit of space. Anything smaller than this cannot be meaningfully described as having a position in space-time. To put that in perspective, the Planck length is to a proton what a proton is to an entire solar system. It's a scale so unimaginably tiny that it makes atoms look like galaxies in comparison. And yet, it is here, at this infinitesimal scale, that the most profound mysteries of the universe unfold. At the Planck scale, quantum gravity becomes the dominant force. Normally, gravity is so weak compared to the other forces that it can be ignored at quantum levels. But when distances shrink toward the Planck length, gravitational interactions between particles become so intense that space-time itself is pulled into violent fluctuations. The smooth continuum described by Einstein's general relativity breaks apart into something chaotic, probabilistic, and discrete. Physicists sometimes describe this domain as space-time foam, a term coined by John Wheeler. Imagine the calm surface of an ocean when viewed from a great height. It looks smooth and flat. But zoom in close enough and you see waves, ripples, bubbles, and turbulence. The same is true for space-time. On cosmic scales, it appears smooth and continuous, allowing planets to orbit stars and galaxies to swirl gracefully through the void. But on the Planck scale, that smoothness disappears. Space and time are thought to bubble and froth with quantum fluctuations, constantly creating and annihilating tiny, transient distortions. Miniature wormholes, black holes, and bursts of energy appearing and vanishing faster than any clock could tick. This foamy nature of space-time implies that the very geometry of the universe isn't fixed, but dynamic and uncertain. Points in space no longer have well-defined positions, and the flow of time becomes ambiguous. The traditional idea of a four-dimensional space-time grid ceases to apply. Instead, reality may be built from discrete chunks or loops of geometry, each one representing the smallest unit of space and time. This is precisely what loop quantum gravity attempts to describe, a theory suggesting that space-time itself is quantized, composed of finite, indivisible elements, much like the pixels of a cosmic hologram. At this level, the interplay between relativity and quantum mechanics becomes unavoidable. Relativity insists that space-time can bend infinitely under gravity, while quantum mechanics forbids infinities altogether. The Planck scale is where these opposing principles collide, a balancing point between the geometric universe of Einstein and the probabilistic universe of quantum theory. It's also the arena where any true theory of everything must operate. Whether it's string theory, loop quantum gravity, or some as yet undiscovered framework, the laws that govern the Planck scale will determine how the cosmos emerged from the quantum chaos of its birth. But this isn't just abstract theory. It has profound implications for understanding reality itself. If space and time are quantized, then the universe is not continuous. It's digital at its deepest level. Just as a movie looks smooth until you zoom in and see the individual frames, the universe might appear seamless only because we are too large to perceive its discrete building blocks. What we call empty space may not be empty at all, but a roiling, energetic medium filled with ephemeral quantum structures, constantly fluctuating and reshaping the geometry of reality. And within that foam, energy densities can spike momentarily to enormous levels, perhaps even spawning tiny, short-lived baby universes, microcosms that pop into existence and vanish again within a Planck instant. Some physicists speculate that our own universe might have begun as one of these fluctuations, a quantum bubble that, through inflation, expanded into the vast cosmos we inhabit today. The Planck scale thus represents more than a limit. It's the threshold between the knowable and the unknowable, between the smooth surface of physics and the turbulent depths beneath. It's where space-time stops being a backdrop and becomes a dynamic, fluctuating participant in the creation of reality. Standing on the edge of the Planck scale, we realize that the universe we experience, the galaxies, the stars, even the flow of time itself, is a kind of grand illusion, built upon quantum foundations that defy all classical intuition. Beneath every atom and every moment lies a restless ocean of space-time foam, boiling with possibility, where the seeds of universes may form and fade in an instant, shorter than 10, raised to the power of -43 seconds. And somewhere in that unthinkably small chaotic sea lies the answer to the question that has haunted physics since Einstein and Planck first peered into the unknown. What is space-time really made of? After exploring the bizarre quantum landscape of the Planck scale, where space-time itself ripples like a restless sea, we step forward into one of the most astonishing chapters of cosmic history, the inflationary epoch. This is the moment when the universe, emerging from its quantum infancy, underwent a mind-bending transformation, a burst of exponential expansion so fast and so vast that it reshaped the entire cosmos in a fraction of a heartbeat. Inflation theory doesn't just explain why our universe looks the way it does. It also opens a Pandora's box of deep, almost philosophical questions about what existed before the beginning we think we know. To grasp the significance of inflation, imagine the universe at roughly 10 raised to the power of -35 seconds after the Big Bang. Just prior to this instant, the cosmos was an unimaginably hot, dense, chaotic quantum field filled with violent fluctuations in energy. According to inflation theory, a mysterious form of energy, known as the inflaton field, suddenly dominated the universe. This field exerted a powerful repulsive pressure, overwhelming gravity itself and driving space to expand exponentially. In an unimaginably short time, the universe doubled in size again and again, possibly 10 raised to the power of 60 times, within less than a trillionth of a second. To put that into perspective, a region smaller than a subatomic particle expanded to a size larger than the observable universe today. During this flash of hyper-expansion, space itself stretched faster than the speed of light. This doesn't violate relativity because it wasn't objects moving through space faster than light. It was space itself expanding, carrying everything with it. The same way dots on the surface of a balloon move apart as the balloon inflates, galaxies, or what would later become galaxies, were swept away from each other by the stretching fabric of space-time. This brief moment of inflation solved several long-standing puzzles that had haunted cosmologists. One of them is the horizon problem, the mystery of why the universe appears so uniform in every direction. The cosmic microwave background, the oldest light in the universe, shows a nearly identical temperature everywhere, even in regions that are so far apart they could never have exchanged information since the Big Bang. Inflation provides a beautiful answer. Before inflation, the entire universe was small enough for all regions to be in thermal contact. Then inflation blew it up so quickly that those regions were flung far apart, preserving their uniformity on enormous scales. Another riddle resolved by inflation is the flatness problem. Observations show that the universe is geometrically flat, meaning its overall curvature is nearly zero. But a flat universe is incredibly unstable. Any tiny deviation from perfect flatness would have grown exponentially over billions of years. Inflation smooths out that curvature, like blowing up a balloon, until its surface appears flat from any local perspective. The result is the vast, flat cosmos we observe today. Inflation also helps explain the absence of magnetic monopoles and other relics predicted by earlier theories of the early universe. The exponential stretching would have diluted such exotic particles to undetectable densities, leaving behind the cleaner universe we now inhabit. Yet, while inflation elegantly explains the large-scale structure of the cosmos, it also raises some of the deepest and strangest questions in physics. Chief among them, what started inflation and what came before it? The theory doesn't tell us where the inflaton field came from or why it began to dominate at that precise moment. Some models suggest it was triggered by a random quantum fluctuation in a pre-existing vacuum state. Others propose that inflation is an eternal process, that our universe is just one bubble in a vast, ever-inflating multiverse. In such models, space never stops inflating entirely. Instead, certain regions cool and pop out of the inflating background, forming isolated universes like ours. Each bubble could have different physical constants, dimensions, or even laws of physics, meaning our reality may be just one of infinitely many. This eternal inflation concept radically redefines the idea of the beginning. If inflation is eternal, there may have been no singular start at all, just an infinite process of creation bubbling endlessly through a quantum sea. What we call the Big Bang, then, would not be the birth of everything, but merely the birth of our local region of space. The true beginning, if it exists, could be hidden beyond our cosmic horizon, forever inaccessible to observation. Inflation also deepens the connection between quantum mechanics and cosmic structure. Remember those tiny quantum fluctuations that dominated the earliest universe? Inflation amplified them to astronomical scales. Regions where the quantum field was slightly denser became the seeds of galaxies and galaxy clusters. Inflation thus transformed quantum uncertainty into cosmic architecture, turning randomness into the scaffolding of reality. Yet, inflation's power comes with an unsettling implication. We may never be able to observe the full consequences of it. Because inflation expanded space faster than light, most of the regions it created are permanently beyond our reach. The observable universe, the portion we can see, is just one small patch of a much larger inflationary landscape. Beyond our cosmic horizon may lie other patches of space-time that evolved differently, obeying variations of the same fundamental rules, or perhaps entirely new ones. In that sense, inflation serves as both a solution and a mystery. It explains the remarkable smoothness and uniformity of our cosmos, but also reminds us of how much we can never know. The event that shaped everything we see may have erased all traces of what came before it. Inflation hides its own origin behind the veil of space-time expansion, leaving us with a universe that remembers only its aftermath. And so, while inflation theory answers many of the how questions of cosmology, it leaves the why hanging in the void. Why did the inflaton field exist? Why did it stop inflating when it did, allowing matter, light, and structure to form? Was our universe a random quantum accident, or the inevitable outcome of deeper laws we have yet to glimpse? Inflation, in all its brilliance and mystery, is the bridge between the unknowable quantum foam of the Planck epoch and the orderly, expanding cosmos we inhabit. It tells us that the universe didn't simply begin, it burst into being, expanding faster than imagination, carving time and space from the raw potential of nothingness. But like all great discoveries in physics, it leaves us staring back into the unknown, wondering whether the story of creation has chapters that lie forever beyond our reach. As we move forward from the explosive birth of inflation, the story of the universe begins to take on an even stranger, more breathtaking dimension, one that stretches beyond the boundaries of everything we can observe or even properly imagine. If inflation truly happened as cosmologists believe, it may not have been a one-time event. Instead, it could still be happening, right now, endlessly, in distant regions of space-time we will never see. This profound idea leads to one of the most fascinating and controversial possibilities in modern physics: the multiverse. The multiverse arises naturally from certain versions of inflation theory, particularly the idea of eternal inflation. In this framework, the inflaton field, the mysterious energy field that drove the early universe's exponential expansion, doesn't decay everywhere at once. Instead, in some regions, it ends locally, allowing those areas to cool, slow down, and form universes like ours. But in other regions, the inflaton continues to drive inflation indefinitely, causing the fabric of space-time to keep stretching faster and faster. Those still inflating regions give rise to more and more local pocket or bubble universes, each emerging with its own initial conditions. Picture a pot of boiling water. Bubbles form randomly throughout, grow and separate from one another. Each bubble is isolated, with its own internal environment, yet all are connected by the same underlying medium. The universe, according to eternal inflation, behaves in a similar way, but instead of bubbles of water vapor, we have bubbles of space-time. Each one is a separate universe, expanding within an eternally inflating cosmic background. Inside our particular bubble, inflation ended long ago. Space cooled, particles condensed, stars formed, and galaxies assembled over billions of years. But beyond our cosmic horizon, inflation may still be raging, spawning new bubbles all the time. Each one potentially infinite in extent, yet causally disconnected from ours. We can never see or touch these other universes, because the space between bubbles expands faster than light can travel. From their perspective, we're just as unreachable. This picture carries staggering implications. If there are countless bubble universes, then the laws of physics themselves may not be universal at all. The constants we take as fundamental, the strength of gravity, the charge of the electron, the speed of light, or even the number of spatial dimensions, could vary from one bubble to another. Our universe might simply be one outcome among endless possibilities, its properties determined by the random quantum fluctuations that occurred when inflation ended here. In some bubbles, stars and galaxies might never form. In others, gravity might be so strong that everything collapses instantly into black holes. There could be universes with different particles, forces, or even exotic forms of matter and geometry beyond our imagination. This idea transforms the nature of physics itself. What we call laws of nature may be local rules, true for our cosmic neighborhood, but not for reality as a whole. This concept finds echoes in string theory, one of the leading candidates for unifying quantum mechanics and gravity. String theory doesn't predict a single, unique universe. It predicts a vast landscape of possible solutions, each corresponding to a different configuration of the extra dimensions it proposes. The number of possible vacuum states in string theory is often estimated at around 10 raised to the power of 500. A nearly unthinkable diversity of universes, each with its own physical constants. If eternal inflation populates this landscape, then every possible version of physics could exist somewhere in the multiverse. Of course, this idea raises a difficult question. If these other universes are forever beyond our observational reach, can we ever truly test the multiverse hypothesis? Science, after all, depends on empirical evidence. And yet, some physicists argue that the multiverse is not just philosophical speculation. It's a logical consequence of our best models of inflation and quantum field theory. If the mathematics predicts such a structure naturally, perhaps it's more reasonable to accept its existence than to arbitrarily declare that our universe is the only one. Moreover, some indirect clues might one day hint at other universes' existence. For instance, if another bubble universe ever collided with ours in the early moments of expansion, the impact might have left subtle imprints in the cosmic microwave background. Strange circular patterns or asymmetries in temperature across the sky. So far, no such evidence has been found, but cosmologists continue to search, knowing that even a whisper of such a signature would revolutionize our understanding of reality. The philosophical consequences of the multiverse are as profound as the scientific ones. If infinite universes exist, then every possible configuration of matter, energy, and history must occur somewhere. There could be versions of you and me in distant bubbles, living slightly or wildly different lives. Somewhere, perhaps, there's a universe where Earth never formed, another where time flows backward, and another where physics itself is so alien that we wouldn't recognize it as existence at all. But the deepest implication of the multiverse isn't about parallel lives or exotic realms. It's about perspective. It suggests that our universe isn't the central stage of creation, but one bubble in an endless cosmic ocean governed by its own local rules. The fine-tuning of the universe, the remarkable balance of constants that allow life to exist, might not be evidence of design, but simply the outcome of cosmic statistics. In an infinite ensemble of universes, even the rarest conditions will inevitably occur somewhere, and we just happen to inhabit one of those lucky regions. And yet, for all its vastness, the multiverse doesn't diminish the mystery, it deepens it. If our universe is one bubble among countless others, what is the medium in which these bubbles form? What governs the inflationary process itself? Is there a deeper level of reality, a meta-universe or cosmic substrate, from which even the multiverse emerges? These questions push us beyond the edge of what physics can currently describe into the borderlands between science and philosophy. Still, they remind us of something essential. Every time we think we've reached the ultimate boundary of knowledge, the universe reveals yet another horizon, receding just beyond our grasp. Perhaps, in the grandest sense, the multiverse is not merely a theory about other worlds. It's a reflection of the infinite capacity of reality to surprise us, to evolve, and to transcend the limits of our imagination. As we journey further outward from the idea of multiple universes, we find ourselves facing a sobering and humbling truth. There are absolute limits to what we can ever know about the cosmos. These limits aren't due to technological shortcomings or lack of ingenuity, but rather to the very structure of spacetime itself. The universe has built-in boundaries to observation, walls of light and time that no telescope, no probe, and no civilization, no matter how advanced, can ever cross. This barrier is known as the cosmic horizon, and it defines the ultimate edge of what's physically knowable. To understand this concept, we need to recall that light has a finite speed, roughly 300,000 kilometers per second. Since the universe has a finite age, around 13.8 billion years, there's only so much distance light could have traveled since the Big Bang. The farthest light that has reached us defines our observable universe, a spherical region roughly 46 billion light-years in every direction. Beyond that, light simply hasn't had enough time to arrive. Those distant regions exist, as far as we can infer, but they are forever hidden from us behind a horizon of causality. However, this horizon isn't a static boundary. It's dynamic and deeply woven into the nature of cosmic expansion. Because the universe has been expanding faster than light can travel in certain regions, there are galaxies and entire structures moving away from us so quickly that their light will never, ever reach us, no matter how long we wait. Space itself is stretching faster than photons can bridge the gap. This means that even though those galaxies might exist within our universe, they are effectively cut off from us forever. We can never communicate with them, never observe them directly, and never know their ultimate fate. This leads to the concept of the cosmic event horizon, distinct from the horizon of the observable universe. The observable universe is defined by what we can see now. The cosmic event horizon defines what we will ever be able to see, even in the infinite future. It represents the outermost shell of spacetime from which light emitted today can still reach us someday. Anything beyond that horizon is permanently inaccessible. As the universe continues to accelerate due to dark energy, that event horizon becomes more restrictive, slowly shrinking our observable portion of reality as distant galaxies slip away beyond it. In essence, the cosmic horizon is a curtain drawn by the universe itself, a boundary that divides what's knowable from what's forever beyond reach. This isn't just a matter of distance, it's a fundamental limit of information. According to relativity, information cannot travel faster than light, which means no signal or observation can ever cross this cosmic divide. The expansion of space ensures that there will always be regions we can never probe, not even in principle. This limit introduces profound implications for cosmology and philosophy alike. For one, it means that our entire scientific understanding of the universe, everything from particle physics to cosmic evolution, is based solely on the tiny fraction of reality inside our horizon. We often speak about the universe as though we're describing the whole of existence, but in truth, we're describing a bubble, a finite sphere of space and time bounded by what light has revealed to us. Beyond that bubble, there could be uncountable galaxies, perhaps even other physical laws or cosmic conditions, but they will forever remain beyond our perception. The cosmic horizon also shapes our understanding of entropy and information density. In physics, information isn't just data, it's a fundamental property of matter and energy. Black hole thermodynamics, for example, teaches us that there's a limit to how much information can be contained within a given region of space. Similarly, our universe's horizon behaves like a cosmic version of a black hole horizon. It defines how much information can be known or stored about our observable cosmos. Some physicists, including Stephen Hawking and Leonard Susskind, have suggested that the universe itself might obey a holographic principle, where all the information about the three-dimensional world inside our horizon could, in principle, be encoded on its two-dimensional boundary. In this view, our entire visible reality may be a kind of holographic projection from that cosmic surface, a staggering idea that blurs the line between physics and philosophy. But perhaps the most unsettling aspect of the cosmic horizon is the inevitability of cosmic isolation. As dark energy drives the universe's accelerated expansion, galaxies far from our local group are racing away at ever-increasing speeds. In the distant future, tens of billions of years from now, most of the galaxies we see today will vanish from view, their light redshifted into oblivion. The universe will appear increasingly empty, leaving behind only the structures bound by gravity, like our local galactic cluster. Future observers living in that far-off epoch might see nothing beyond their own galaxy and conclude, incorrectly, that the cosmos is small, static, and lonely. This haunting prospect underscores the fragile privilege of our cosmic moment. We live in an age when the universe is still readable, when the light from its birth still reaches us, carrying ancient messages from the dawn of time. We are, quite literally, cosmic archaeologists, peering across the greatest distance and oldest light that reality allows. Yet, as we gather data and refine our theories, we must accept that there will always be an outer darkness, a realm beyond even the reach of thought, where the universe continues unseen and unmeasured. In that sense, the cosmic horizon isn't merely a physical limit. It's a mirror reflecting the limits of knowledge itself. No matter how advanced our science becomes, there will always be a frontier beyond which we cannot go, a veil drawn by nature, reminding us that understanding is not the same as omniscience. The cosmos invites exploration, but guards its deepest secrets behind the horizon, ensuring that mystery endures as part of existence's very fabric. And so, when we speak of the universe, we must do so humbly. What we truly mean is our observable universe, a single luminous bubble floating in an unfathomably vast, possibly infinite reality. Beyond the horizon lies a realm we will never touch, never see, and never know. An endless sea of cosmic possibility, forever beyond the reach of light, time, and imagination. As we gaze back toward the very beginning of the universe, past galaxies, past atoms, past even the earliest quantum fluctuations, we eventually arrive at a point where not only matter and energy dissolve, but time itself begins to lose meaning. In everyday life, time feels like the most reliable thing there is. It flows, it orders events, it gives structure to our thoughts and actions. We talk about before and after, past and future, as though time were a river running eternally forward. But when we trace the cosmos back to its origins, physics begins to whisper a radical and unsettling truth. Time may not have existed before the Big Bang. This idea emerges from both Einstein's relativity and quantum cosmology. According to general relativity, time is not a separate, universal backdrop against which events unfold. It is a dimension woven together with space into the fabric of spacetime. Matter and energy shape that fabric, curving it to produce gravity. But if we follow relativity backward through the expanding universe, all matter and energy compress into a singularity, a state of infinite density where space-time itself breaks down. At that singularity, the equations of relativity no longer work, because the very fabric they describe ceases to exist. And if space-time doesn't exist, neither does time as we know it. In other words, time begins with the universe. There was no before the Big Bang, because before is a concept that only makes sense within time. Asking what came before the Big Bang is like asking what's north of the North Pole. It's a question that dissolves once you understand the geometry. The Big Bang was not an explosion in time. It was the moment when time itself began to flow. This idea forces us to rethink causality, the principle that underlies all of science, the belief that every effect has a cause. In the world we inhabit, cause and effect are inseparable. They define the arrow of time. But if time began at the Big Bang, then the universe itself has no cause in the traditional sense. There was no before in which a cause could exist. The universe didn't happen in time, it brought time into being. As Stephen Hawking once said, The question, what happened before the Big Bang, is meaningless because there was no time for anything to happen in. Yet, this doesn't mean the universe emerged from absolute nothingness. The phrase nothing in cosmology is slippery. In quantum theory, what we call nothing can still have structure, fields, energy fluctuations, even potential laws of physics. Some models suggest that the universe could have emerged from a quantum vacuum, a state of lowest possible energy, through a spontaneous fluctuation governed by quantum uncertainty. In this picture, the universe didn't require a before. It emerged as a timeless quantum event, with time itself crystallizing only after expansion began. In fact, in quantum cosmology, time might be an emergent property rather than a fundamental one. The equations that describe the universe at its smallest scales, such as the Wheeler-DeWitt equation, don't include time at all. They describe a static, timeless reality where all possible configurations of the universe coexist in a kind of quantum superposition. In that view, time arises only when certain relationships between parts of the universe become meaningful, when change is observed. As the universe expands and structures form, these relationships define what we perceive as temporal flow. Time, then, isn't a universal backdrop. It's a product of interaction, a measure of change, a pattern that emerges from chaos. This concept, that time is emergent, finds resonance in both quantum gravity and thermodynamics. According to Entropy, time's arrow points in the direction of increasing disorder. In the early universe, entropy was extraordinarily low, an almost perfectly ordered state. As the universe expanded and cooled, entropy increased, giving rise to the flow of time as we experience it. In other words, time's direction may simply reflect the universe's evolution from order to disorder. Without that imbalance, there might be no distinction between past and future at all. At the edge of cosmic beginnings, these distinctions blur completely. Before and after, cause and effect, they all lose meaning when time itself becomes undefined. Even the concept of age becomes nonsensical, because there's no external clock against which to measure the passage of moments. At the Planck epoch, when the universe was smaller than 1.6 times 10 raised to the power of -35 meters, spacetime was so turbulent that there may have been no continuous flow of time. Only quantum fluctuations in geometry, blinking in and out of existence like sparks on a cosmic circuit board. This challenges not only physics, but also our deepest intuitions about existence. We humans experience life as a sequence, a story unfolding moment by moment. But the universe may not share that perspective. At its most fundamental level, it might not experience time at all. It simply is. Past, present, and future could all coexist in a timeless whole, like the frames of a film reel viewed all at once. What we perceive as the flow of time may just be our limited way of navigating this vast, static cosmic structure, a reflection of consciousness interacting with the universe's geometry. And so, when we say that time began with the Big Bang, we are acknowledging not only the birth of motion and change, but the birth of meaning itself. Causality, sequence, history, all the things that make sense to us, emerged from a timeless quantum reality that preceded them. The Big Bang wasn't the beginning of everything. It was the beginning of becoming. In this light, the universe's origin is not a singular event, but a transition, from timeless potential to temporal existence, from pure possibility to unfolding reality. Time, rather than being an eternal river, may be a ripple on the surface of a deeper, timeless sea, a temporary illusion woven into the fabric of spacetime, destined to fade when the cosmos itself reaches its final equilibrium. And as we stand here, suspended in that flow, we realize that we are both part of time and outside of it, beings of entropy and energy, conscious patterns born from the moment when time itself first opened its eyes. If time itself is one of the great mysteries of the cosmos, then its direction, the fact that it flows only forward, is perhaps the most profound of all. Every moment we live, every experience we remember, every breath we take, moves irreversibly from past to future. We cannot unmix cream from coffee, unsmash a glass, or unburn a star. This one-way movement of time, the so-called arrow of time, defines our very experience of reality. But physics, in its deepest equations, doesn't actually demand it. The laws that govern motion, electromagnetism, and even quantum mechanics are time-symmetric. They work just as well backward as forward. So why then does the universe move only one way? Why does time flow forward and not backward? The answer lies in a concept as old as thermodynamics itself: entropy. Entropy is, in simple terms, a measure of disorder, or more precisely, the number of possible microscopic arrangements of a system that correspond to its macroscopic state. A deck of cards sorted in order has low entropy. A shuffled deck has high entropy. The same goes for the universe. When it began, it was astonishingly ordered, a state of extremely low entropy. Over time, as energy spreads out and systems become more mixed and randomized, entropy increases. And that increase, described by the second law of thermodynamics, gives time its arrow. Here's how it works. Every process that occurs in nature, heat flowing from hot to cold, stars burning fuel, galaxies forming and collapsing, moves from states of lower entropy to higher entropy. Once energy spreads out, it can't spontaneously reconcentrate without external input. This tendency toward increasing disorder is what gives the universe a sense of progression, a before and after. It's what allows cause and effect to exist. In a perfectly symmetric, timeless universe, there would be no change, only stasis. But because entropy rises, time moves forward. The universe evolves. The truly baffling question, however, isn't why entropy increases. It's why it started so low in the first place. According to the Big Bang model, the early universe was a hot, dense plasma in near-perfect thermal equilibrium, everything mixed uniformly. By ordinary thermodynamic standards, that sounds like high entropy. But when gravity enters the picture, things get tricky. Unlike most forces, gravity tends to clump matter together, not spread it out. A smooth, homogeneous distribution of matter is actually low gravitational entropy because it represents an unstable, highly ordered state. As the universe expanded, gravity began pulling matter into clumps, galaxies, stars, planets, driving entropy upward. So our universe began in an extraordinarily special configuration, smooth, uniform, and balanced to an almost impossible precision. The British physicist Roger Penrose once estimated that the probability of the universe starting in such a low entropy state was roughly 1 part in 10 to the power of minus 37. 10 raised to the power of 10 raised to the power of 123. A number so incomprehensibly small, it defies imagination. This precision is what allowed time, as we know it, to exist at all. But why was the early universe so orderly? That remains one of the deepest unsolved puzzles in cosmology. Some physicists argue that inflation, the brief exponential expansion after the Big Bang, may have smoothed out the cosmos, erasing irregularities and lowering entropy. Others suggest that our notion of entropy might need rethinking when applied to the entire universe. There are also radical ideas that time itself might be emergent, and that the arrow of time arises from boundary conditions at both the beginning and the end of the cosmos. Another possibility is that entropy and time are two sides of the same coin. Perhaps the low entropy start of the universe wasn't a coincidence, but a necessary condition for time to exist in the first place. In that view, the universe didn't begin in time. It began with time, and the arrow of time was born in that same moment. The progression from order to disorder is what creates the very perception of temporal flow. Without entropy increasing, there would be no meaningful sense of before or after. The cosmos would be static, frozen, a timeless equilibrium with no memory, no causality, no becoming. Entropy doesn't just govern cosmic evolution, it governs us. Every heartbeat, every thought, every act of remembering is a tiny contribution to the universe's rising entropy. Our brains process information by dissipating energy, turning ordered chemical potential into heat. Memory itself is an irreversible act. To remember is to create entropy. In that sense, the arrow of time isn't just cosmic, it's biological and psychological. We feel time's passage because our existence depends on irreversible processes. Yet, entropy's relentless rise also gives time its poignancy. It points us toward the inevitable, a future where energy becomes evenly distributed, stars burn out, and the universe approaches heat death, a state of maximum entropy where no more useful work can be done. In such a future, time might lose its meaning again as change ceases and the cosmos drifts into eternal equilibrium. There's a strange symmetry in that idea. The universe began in a low entropy, highly ordered state, a cosmic spring wound, tight with potential. As it unwinds, energy flows, galaxies form, life emerges, and consciousness arises to witness it all. And then, gradually, everything returns to stillness. In the grand arc of cosmic history, time itself may be a temporary phenomenon, a flicker between two timeless eternities, the perfect order of the beginning and the perfect disorder of the end. So when we look at a clock, or watch the sun set, or grow older, we are really witnessing the deep thermodynamic truth that governs the universe. Time moves forward because entropy increases. The arrow of time is not an illusion, but a shadow cast by the universe's inexorable journey from simplicity to complexity, from order to chaos. And somewhere in that journey, between the symmetry of the early cosmos and the silence of the distant future, time became a stage on which existence could unfold, briefly, beautifully, before returning to the stillness from which it came. As we step deeper into the fabric of the universe, past the mysteries of entropy and the arrow of time, we inevitably encounter one of the greatest unfinished quests in science, the search for a theory of quantum gravity. This is the ultimate bridge between the two great pillars of modern physics: Einstein's general relativity, which describes gravity and the curvature of space-time on cosmic scales, and quantum mechanics, which governs the behavior of particles and forces at the smallest scales. Both theories are remarkably successful in their respective realms, but when we try to apply them together, at the extremes of black holes or the Big Bang, they violently disagree. The need for quantum gravity arises precisely because the universe refuses to stay compartmentalized. Gravity, though weak on the quantum scale, becomes dominant at high energies and small distances, such as the Planck length, around 1.6 times 10 raised to the power of minus 35 meters. At that scale, the gravitational curvature of spacetime becomes as intense as quantum fluctuations themselves. The result is chaos. Relativity's smooth spacetime fabric and quantum theory's jittery uncertainty collide, producing mathematical infinities and physical nonsense. To move beyond this impasse, physicists have developed several ambitious frameworks that aim to unite gravity and quantum mechanics into a single, consistent theory, one that can describe the earliest moments of the universe and the interiors of black holes without breaking down. Two of the leading contenders are string theory and loop quantum gravity. Let's start with string theory, perhaps the most famous and far-reaching attempt to reconcile the quantum and the cosmic. String theory proposes that the fundamental building blocks of reality aren't point-like particles, as quantum field theory assumes, but rather incredibly tiny, one-dimensional strings of vibrating energy. The different vibrations of these strings give rise to all known particles, electrons, quarks, photons, as well as the forces that govern them. In this picture, what we perceive as different particles are simply different notes played by the same cosmic instrument. One of string theory's most revolutionary insights is that gravity emerges naturally from its equations. When strings vibrate in specific ways, they produce a particle called the graviton, a hypothetical quantum carrier of the gravitational force. In ordinary quantum field theory, gravity refuses to be quantized without producing infinite, nonsensical results. But in string theory, because strings have finite size, those infinities are smoothed out. The theory doesn't just tolerate gravity, it requires it. However, string theory also demands something extraordinary: additional dimensions. For the mathematics to work consistently, spacetime must have not 4 dimensions, 3 of space and 1 of time, but 10 or even 11. The extra dimensions, according to theory, are curled up into unimaginably tiny shapes known as Calabi-Yau manifolds, compact, intricate geometries that define the properties of our universe. The way these extra dimensions are folded may determine the values of physical constants, the types of particles that exist, and the strengths of the fundamental forces. This leads to one of string theory's most mind-bending implications, the so-called string landscape. There are potentially 10 raised to the power of 500 different ways these dimensions could be compactified, each corresponding to a different possible universe. This connects deeply to the concept of the multiverse discussed earlier, suggesting that our universe is just one realization among an almost infinite set of possibilities, each governed by different physical laws. Despite its elegance, string theory faces a major challenge. It's nearly impossible to test experimentally. The energy scales at which its predictions become evident are far beyond the reach of any particle accelerator we can build. This has led some critics to call it a mathematical dream, beautiful but unprovable. Still, many physicists believe it's the best candidate we have for a complete theory of everything, a framework that could, in principle, explain every particle, force, and constant in the universe. But string theory is not the only path. Another promising approach takes a very different route: loop quantum gravity, LQG. Where string theory introduces new objects and dimensions, loop quantum gravity works directly with the fabric of spacetime itself. It seeks to quantize geometry, to describe space and time not as continuous, smooth entities, but as discrete, granular structures composed of tiny loops or quanta of spacetime. In LQG, spacetime is built from fundamental units, like atoms of space, connected in a network known as a spin network. These loops form an ever-changing web, evolving in time to create the appearance of a continuous universe. But at the smallest scales, space is not smooth. It's pixelated, like a holographic grid. This granularity eliminates the infinities that plague general relativity and prevents the formation of true singularities. One of LQG's most remarkable predictions is that the Big Bang singularity might not have been the beginning at all. Instead, it could have been a big bounce. As the universe contracts under gravity, quantum effects counteract the collapse before reaching infinite density, causing the universe to rebound and expand again. If true, this means our universe could be cyclic, eternally oscillating between expansion and contraction, with each bounce erasing but also preserving traces of the previous cosmos. Unlike string theory, Loop quantum gravity doesn't require extra dimensions or unseen entities. It modifies the very geometry of spacetime itself. Its strength lies in its conceptual simplicity and mathematical rigor, but its weakness is that it doesn't naturally unify all the forces of nature. It beautifully describes gravity at the quantum level, but leaves electromagnetism and the nuclear forces untouched. Beyond these two giants, there are other contenders and hybrid ideas. Causal dynamical triangulations, CDT, asymptotic safety, non-commutative geometry, and even attempts to merge insights from both string theory and loop quantum gravity. Each approach is a different language, trying to describe the same ineffable truth. What happens when the fabric of space-time itself becomes quantum? Ultimately, all these efforts aim at one goal: to find the theory that will make sense of the universe's first instant and its most extreme conditions. Quantum gravity is not just about uniting two branches of physics. It's about uniting the small with the vast, the uncertain with the geometric, the probabilistic with the deterministic. It's about understanding the moment when reality itself turned from mathematics into matter, from probability into presence. When we finally discover the true theory of quantum gravity, if we ever do, it will not only rewrite the equations of physics, it will rewrite the story of existence itself, revealing what really happened before time began, and whether the cosmos we know is just one thread in a much larger, multi-dimensional tapestry. When we talk about the edges of the universe, the Big Bang, black holes, and the cosmic horizon, we're not just talking about the boundaries of space and time. We're also talking about the boundaries of human knowledge. These are the frontiers where our equations falter, where the smooth certainty of physics fractures into paradoxes, infinities, and unknowns. In a very real sense, these edges act as stress tests for reality itself. The places where the universe exposes the weaknesses of our theories and challenges us to think deeper about what understanding truly means. In science, failure is not defeat, it's a compass. Every time our models reach their breaking point, they point the way toward new discoveries. The Big Bang, black holes, and cosmic horizons are not merely mysteries, they are laboratories for testing the limits of physics. Each one highlights a tension between the two great frameworks we rely on to describe existence: general relativity and quantum mechanics. Let's start with the Big Bang, the ultimate cosmic edge. According to general relativity, if we trace the expansion of the universe backward, everything converges into an infinitely dense point, a singularity. But singularities are, in a sense, the universe's way of saying, stop. Your math no longer applies here. They're not physical objects, but boundaries of predictability. Regions where the equations give infinite answers and the laws of physics as we know them cease to function. This is the first stress test of our understanding. Relativity tells us how space-time curves and evolves, but when it encounters infinite density and zero volume, it collapses mathematically. The singularity is not a place. It's a signpost pointing toward the need for a deeper quantum theory of gravity. Then there are black holes, those dark, gravitational abysses scattered across the universe. They represent another kind of edge, a local singularity hidden behind an event horizon. Inside a black hole, gravity crushes matter into a state so dense that not even light can escape. Relativity predicts that space-time continues collapsing inward endlessly. But quantum mechanics tells a different story. It refuses to allow information to be destroyed. This leads to the infamous black hole information paradox, a crisis born from the clash between the continuous, geometric world of relativity and the discrete, probabilistic world of quantum theory. Hawking radiation, a quantum effect near the event horizon, complicates the story further. If black holes can evaporate, as Stephen Hawking predicted, then what happens to the information about the matter that fell in? Does it disappear forever, violating quantum law? Or is it somehow preserved, encoded on the event horizon, or released as radiation? This paradox has driven some of the most creative work in theoretical physics, giving rise to ideas like the holographic principle, which suggests that all the information inside a volume of space can be represented on its boundary surface. Once again, the edge becomes the teacher. The boundary of a black hole may hold the key to understanding quantum spacetime itself. At the largest scales, we encounter another kind of boundary, the cosmic horizon, the limit of what we can observe. Beyond this horizon, the expansion of the universe carries galaxies away faster than light can travel, cutting them off from us forever. This horizon is not a wall, but a limit of information. It defines the observable universe, the finite patch of reality accessible to us. We can't see beyond it, measure beyond it, or even be sure what exists beyond it. Yet, the very existence of such a limit forces us to confront a profound question. Is physics universal, or is it local to our observable bubble? The cosmic horizon challenges one of science's oldest assumptions, that the universe operates according to universal laws that apply everywhere at all times. If we can never observe beyond a certain region, can we ever know for sure that our laws of physics apply beyond that boundary? Perhaps there are other regions, unobservable but real, where different constants, particles, or even space-time structures exist. The edge of observation thus becomes the edge of certainty, where science shades into philosophy. In all of these examples, the Big Bang, black holes, the cosmic horizon, what we call edges are really mirrors, reflecting the limits of our theories back at us. Relativity and quantum mechanics have guided us astonishingly far, but at these frontiers, they start to contradict each other. Time behaves unpredictably, space warps beyond comprehension, and cause and effect blur into uncertainty. These are not flaws of the universe. They are flaws in our map of the universe. The cosmos itself is perfectly consistent. It is our descriptions that break down. That breakdown, however, is the engine of progress. Every revolution in physics, from Newton to Einstein to quantum theory, was born from a failure at an edge. Newton's laws worked beautifully until they reached the speed of light. Einstein's relativity worked perfectly until it reached the quantum scale. Now, at the boundaries of the Big Bang and black holes, nature is calling us again, urging us to unify these seemingly incompatible views into a single, coherent framework. And this is what makes the edges of the universe so vital. They are not places of ignorance, but frontiers of potential. The singularity, the horizon, the unobservable, these are the places where our understanding thins and where the next breakthroughs are likely to emerge. The equations that fail there are not failures of reason, but signs that reason has reached its current horizon, ready to expand. In this way, the edges of the universe are not just boundaries of space, they are boundaries of thought. They challenge our definitions of reality, time, information, and even existence itself. They remind us that science is not about having all the answers, but about continually pushing against the edges of the unknown, peeling back one layer of mystery at a time. Every time physics breaks down, it doesn't mark an end, it marks a beginning. Each paradox is an invitation, each horizon a promise that beyond it lies a deeper order waiting to be discovered. The universe, in its vastness, doesn't hide its secrets maliciously. It reveals them gradually through the cracks in our understanding, one mystery at a time. And so, when we speak of the edges of physics, we are really speaking about the edges of ourselves, our curiosity, our imagination, our will to explore. The universe tests our knowledge not to defeat us, but to inspire us to evolve, to see farther, to think bigger, and to dream beyond the horizon. When we peer into the night sky, gazing through telescopes that can capture light invisible to human eyes, we are not just looking outward into space, we are looking backward in time. Every photon that reaches us carries a story, a record of where it came from and how long it has been traveling. The farther we look, the older that light is, and the closer we come to witnessing the universe as it was in its infancy. But there is a limit to how far back we can see, and at that ultimate frontier of visibility lies one of the most extraordinary discoveries in modern science: the cosmic microwave background radiation, or CMB, a faint, ancient glow that acts as the fossil light of creation. The CMB is the oldest light we can observe, a whisper from the time when the universe was just about 380,000 years old. Before that moment, the cosmos was unrecognizable, an opaque, roiling plasma of particles, photons, and radiation so hot and dense that light couldn't travel freely. Photons constantly scattered off electrons and protons, bouncing around in a cosmic fog. The universe was, quite literally, glowing, but that light couldn't escape. Then, something remarkable happened. As the universe expanded, it cooled, dropping below a critical temperature of about 3,000 kelvins. At that point, free electrons and protons began to combine into neutral hydrogen atoms, a process called recombination. Once the electrons were captured, photons no longer scattered as easily, and the universe suddenly became transparent. Light, for the first time, could travel freely through space. Those first free photons began streaming in all directions, and they've been traveling ever since. We detect them today as the CMB, discovered accidentally in 1965 by Arno Penzias and Robert Wilson, who were investigating what they thought was noise in their radio antenna. The CMB turned out to be one of the most important observations in all of cosmology. It provided stunning confirmation of the Big Bang theory, revealing that the universe did, in fact, begin from a hot, dense state and has been expanding and cooling ever since. When scientists study the CMB, they're essentially seeing a snapshot of the universe's baby picture, frozen in time when it was less than 400,000 years old. That may sound ancient, but compared to its current age, 13.8 billion years, it's like looking at an infant photo of an adult. The CMB comes to us from a distance of about 46 billion light-years, because the space through which that ancient light traveled has been expanding all the while. At first glance, the CMB appears remarkably uniform, the same in every direction to about 1 part in 100,000. This near-perfect smoothness tells us that the early universe was incredibly homogeneous, with only the tiniest variations in density and temperature. And yet, those slight variations, the faint ripples in the CMB's glow, carry the seeds of everything that would follow. The denser regions would later grow under gravity's pull, forming galaxies, clusters, and the cosmic web that stretches across space today. In other words, every star, planet, and living being traces its origins back to the tiny temperature fluctuations recorded in the CMB. Over the decades, satellites such as COBE, WMAP, and Planck have mapped the CMB with ever-increasing precision, revealing a detailed pattern of these temperature variations. Tiny hot and cold spots spread across the entire sky. These maps are nothing less than a blueprint of the early universe, encoding information about its composition, geometry, and fate. From them, cosmologists have measured the proportions of the universe's contents: roughly 5% ordinary matter, 27% dark matter, and 68% dark energy. They've also determined that the universe is spatially flat to an astonishing degree, consistent with the predictions of inflationary theory. Even more remarkably, the CMB carries polarization patterns. subtle alignments in the direction of its light waves that tell us about events that happened long after recombination. As the first stars formed and their radiation rayonized the intergalactic medium, these photons left faint imprints on the CMB's polarization, allowing scientists to trace the timeline of cosmic rayonization. Some polarization patterns, known as B modes, might even hold clues to the universe's earliest moments, traces of primordial gravitational waves produced during inflation itself. Detecting those would be like hearing the universe's first heartbeat, a direct echo of the instant it was born. The CMB, in essence, is a cosmic time capsule, carrying within its faint microwave glow the fingerprints of the universe's origin and evolution. It has allowed physicists to test cosmological models with incredible precision, turning the Big Bang from a theoretical idea into a robust scientific framework. Through it, we've learned that space has been expanding for billions of years, that the cosmos began in a hot, dense state, and that it will likely continue to expand indefinitely. But the CMB also reminds us of the limits of sight. Beyond the surface from which that light was released, the so-called last scattering surface, the universe remains forever hidden. Before recombination, the cosmos was opaque, so no light can come to us from earlier times. To see further back, to glimpse the moment of the Big Bang itself, we would need a new kind of messenger, perhaps gravitational waves or neutrinos that can travel unimpeded through the densest conditions. Efforts are underway to detect these relic signals, but so far they remain tantalizingly out of reach. Still, it's awe-inspiring to realize that every time you tune a radio between stations and hear that faint hiss of static, a small fraction of that noise, about 1%, is actually the cosmic microwave background. It is ancient light, billions of years old, washing over you from all directions, a soft whisper from the dawn of time. Through the CMB, we don't just observe the early universe, we commune with it. We see the frozen echoes of a moment when the cosmos first became visible, when light broke free from matter and began its long journey across time to reach us. And in that faint, persistent glow, we find something profoundly human. The story of beginnings, written in light, waiting patiently across eternity to be read. When we look deep into the universe, past the great clusters of galaxies and into the faintest reaches of the cosmic horizon, something extraordinary reveals itself, something that seems, at first glance, impossible. Many of those distant galaxies we observe are receding from us faster than the speed of light. That simple statement sounds like a direct violation of Einstein's theory of relativity, which tells us that nothing can move faster than light in a vacuum. Yet, this superluminal recession is not only possible, it's a natural consequence of the way the universe expands. The key lies in understanding one crucial distinction. It's not galaxies moving through space that are outrunning light. It's space itself that's expanding. To grasp this concept, imagine space not as a static stage upon which the universe's drama unfolds, but as a dynamic fabric, a flexible, stretchable medium that can grow, bend, and curve. This is the picture Einstein's general theory of relativity gives us. Space and time are interwoven into a single entity, spacetime, and it can change its geometry in response to matter and energy. When cosmologists say the universe is expanding, they don't mean galaxies are flying apart through empty space like shrapnel from an explosion. Instead, the space between galaxies itself is stretching. A classic analogy is the balloon model of the universe. Picture galaxies as dots on the surface of an inflating balloon. As the balloon expands, the dots move away from one another, even though none of them are moving across the surface. The distance between them grows simply because the surface itself is expanding. If you were a two-dimensional being living on that balloon, you'd see every other galaxy receding from you, and the farther a galaxy was, the faster it would appear to move away. There's no center of expansion. Every point sees the same effect. Our universe behaves similarly, except in 3 dimensions rather than 2. This relationship is described mathematically by Hubble's law, discovered by Edwin Hubble in the 1920s. It states that the recessional velocity of a galaxy, how fast it appears to be moving away from us, is proportional to its distance from us. V equals h0 times d. Here, v is the velocity, h0 is the Hubble constant, and d is the distance. For nearby galaxies, this velocity is relatively small compared to the speed of light. But as distances grow vast, billions of light years, this simple relationship predicts recessional speeds that exceed the speed of light. At first, that seems to contradict relativity, but it doesn't. Einstein's theory forbids objects from moving through space faster than light, but it places no such restriction on the expansion of space itself. The galaxies are not breaking any cosmic speed limits. They remain stationary in their local regions of spacetime, while that spacetime stretches in between them. Relativity governs the motion of objects within space, not the global dynamics of the space's expansion. To put it another way, imagine 2 ants sitting on the surface of a balloon as it inflates. Each ant is stationary on its patch of rubber, yet as the balloon expands, the distance between them grows. If the balloon inflates fast enough, the ants can be carried apart faster than any speed they could crawl. The ants haven't broken any rules. They've simply been swept along by the balloon's expansion. Now, let's take that idea to cosmic scales. The universe has been expanding ever since the Big Bang, but this expansion is not uniform through time. Early on, gravity slowed it down as matter clumped together. Then, a few billion years ago, something unexpected happened. The expansion began to accelerate. The cause, as we now understand it, is a mysterious form of energy that permeates space itself, dark energy. It acts as a kind of repulsive pressure, driving the universe to expand faster and faster. Because of this accelerating expansion, galaxies beyond a certain distance, roughly 14 billion light-years away, are receding from us faster than light. This has startling consequences. Light emitted today from those galaxies will never reach us. In fact, even light that's already been traveling toward us for billions of years might never make it if the expansion outruns it. Those regions of space are effectively cut off from our observable universe. The galaxies within them will fade from view as their light becomes stretched, redshifted, beyond detectability. Eventually, even the most distant visible galaxies will vanish, leaving behind a lonely, darkening cosmos. And yet, this doesn't mean those galaxies have disappeared in any absolute sense. They still exist in their own regions of spacetime, governed by their own local physics. It's just that the expanding fabric of the universe ensures that no signal, no photon, no information from them can ever reach us again. The universe is like a grand, ever-growing stage where the actors recede beyond the spotlight, not because they're moving faster than light, but because the stage itself is expanding beneath their feet. This concept leads to one of the most beautiful and haunting ideas in cosmology, the cosmic event horizon. Just as a black hole has a boundary beyond which light cannot escape, our universe has a boundary beyond which light can never reach us. It's a horizon not of gravity, but of expansion. Everything beyond it is, for all practical purposes, unreachable and unknowable. It's a humbling reminder that we live in a finite observable bubble within an infinite, or at least vastly larger universe. What we see through our telescopes is not the whole story, only the portion of the cosmos that light has had time to reveal. Beyond that horizon, the universe may continue endlessly, filled with uncountable galaxies forever lost to us. And yet, there's something profoundly poetic about this. The very expansion that will one day hide the distant galaxies from view is also what made them visible in the first place. The stretching of space not only carries light away, but also brings it to us, redshifted and ancient, carrying the memory of a younger universe. So, when we speak of galaxies receding faster than light, we're not witnessing the breaking of physical law, but the graceful stretching of reality itself. The universe is not static, it's alive, dynamic, and expanding in a way that defies everyday intuition. Relativity isn't violated, it's vindicated, for it is relativity that allows us to understand how space and time themselves can evolve. In the end, the accelerating expansion of the universe isn't just a cosmic curiosity, it's a profound statement about the nature of reality. Space and time are not immutable containers, but participants in the cosmic story, expanding faster than light, not because they disobey the laws of physics, but because they are the laws of physics unfolding. As we near the end of our exploration, we must face a deeper question, one that transcends equations and telescopes. Are concepts like the beginning or the edge of the universe truly real? Or are they simply the limits of our perception and imagination? Every scientific model we've built, from the Big Bang to cosmic inflation, rests on human notions of cause, time, and boundary. Yet, the universe may not be beholden to those ideas at all. When we speak of the beginning, we imply a moment of creation, a first instant. But if time itself is part of the universe, then before has no meaning. Likewise, when we imagine an edge, we picture a border, a place where something ends and something else begins. But cosmology tells us there is no edge in space. It curves back on itself, infinite or boundless, depending on the model. Perhaps our minds, evolved to navigate finite experiences, impose edges where none exist. It's possible that both the beginning and the edge are illusions of perspective, artifacts of limited human cognition, trying to grasp an infinite, timeless reality. The Big Bang might not be the birth of everything, but merely the horizon of our knowledge. Beyond it could lie realms we cannot conceive. Maybe then, the universe has no start or border at all, only transitions, transformations, and infinite depth. In this view, existence isn't a line with endpoints, but a vast, self-sustaining whole, cycling through forms of energy, matter, and consciousness. And perhaps the weirdness we see at the universe's limits isn't the cosmos failing to make sense. It's us discovering the limits of the tools we use to understand it. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.